Hello everybody, this is Dr. Christopher White and welcome to today's presentation, which is going to be on geologic time. Alright, let's get going. So how do we measure geologic time? So there are two methods which we can employ to measure geologic time. We can use relative dating or numerical dating. Now, numerical dating is the most straightforward. Essentially what we do is we take a piece of rock, we analyse it using its radioactive isotopes, and we use those radioactive isotopes to calculate an age, an actual number for the rock. So that one's all relatively straightforward. Relative dating, on the other hand, isn't quite so simple. So relative dating uses the relationships between layers of rock to interpret which layer of rock came first, second, third, fourth. So essentially you don't actually get any numbers. What you get is you get a sequence of rock. So you get a sequence of events which occurred to produce the layers of rock that you can see in front of you. So once again, relative dating, no number; numerical dating, number. The problem is that numerical dating wasn't really available until the 1940s. More accurately, it wasn't available on a large scale until the 1970s. And so this means that most geologists, especially geologists who were, starting to produce the main theories that, underlie modern geology, well, they could only date rocks in a relative way. And so they use the relationships between the rocks and the fossils in those rocks to help split the rocks up into different units. So the next question is well, what exactly was used to split up the geologic timescale? Well, the answer is quite simply fossils. So if you look at your geologic timescale, what you'll see is it's split into, the Cambrian, the Ordovician, Silurian, Devonian, Carboniferous, Permian, Triassic, Cretaceous, etc. So the boundaries between the eras, the eons, the ages, the epochs, etc., they are essentially mostly based on fossils. So, at each of those boundaries, a key fossil or fossils will either appear or disappear from the fossil record. And so we have a visual cue that we've crossed that boundary. So let's take the boundary between the Cretaceous and the Tertiary. So that's 66 million years ago. Well, obviously below that boundary we have dinosaurs. As soon as you go above that boundary, no dinosaurs. So we have a visual cue in our sequence of rocks that tells us that we've crossed the boundary. So the geologic timescale is dominantly based on fossils. Now this means that if you look at your geologic timescale and you see all those numbers on, going down your geologic timescale that tells you, for instance, that the Cretaceous-Tertiary boundary was 66 million years ago, well, those numbers are only very, very recent additions. The actual geologic timescale itself was created, a couple of hundred years before that, and it's based exclusively on fossils. Now, obviously, there is one minor problem, of course, is that fossils didn't really start occurring in a big way until about 541 million years ago. So anything that's older than 541 million years, well, we have ourselves a bit of a problem because there are no, large fossils. They're all microfossils. And so that means that rocks which were older than 541 million years were very difficult to date for these early geologists. And by dating, I mean put in a relative dating situation. And so what they did is they decided to say, right, well, we don't really know what's going on here, so we're just going to take all these fossil-free rocks and we're just simply going to refer to them as the Precambrian. And so if you ever look at the geologic timescale, you'll realise that the Precambrian is huge. It's from about 4.5 billion years to 500 million. So it's about 4 billion years in size. It's massive. And, the geologists at the time didn't realise how big the Precambrian was, because remember, they couldn't get numerical dates for the rocks they were looking at. And so, that's resulted in this Precambrian, which is absolutely huge, whilst the Phanerozoic, comparatively speaking, is tiny. It's about 1/8 the size. So the geologic timescale is based on relative dating, and numerical dating is only a relatively recent addition. So let's, while thinking about geologic time, let's go all the way back to the beginning. Okay, so initial models of time were based on what's called circular time, also sometimes called eternal return. So the classical basis for this model is that the sun and the moon appear each day, the seasons come and go, and the year always starts at the same point. So everything follows a defined pattern, from which it doesn't really deviate, at least on a human timescale. And so, people just drew the conclusion that time was moving in a circular fashion because, let's face it, the day started anew each time. The lunar cycle restarted, the year restarted, etc. So things didn't really change. And so there were also some people that said, well, the only reason you get old is because you think you're getting old. Because remember, time doesn't really exist. It's all circular. So if everyone's working under the idea that time starts afresh each day, or that you can control it just by thinking about it, the idea of a relative time can't really exist. So the idea that a rock face, or the rocks that make up that rock face, represent the passage of time just doesn't compute. So in the Western world, the idea of linear time didn't begin to take hold until Christian scholars tried to establish the date of the creation using the Bible. And using the Bible, a gentleman called James Ussher, who was the Bishop of Armagh in Ireland, declared that God created the earth on Sunday the 23rd of October 4004 BC. And so this is essentially using the Bible and just working backwards through the Bible and essentially ending up at this date. And so this gives us linear time. So essentially it says, right, this is when the earth was created, and then time moved forward from this point. So this became the established date, and it held until the late 18th to early 19th century. So that would mean that the earth was about 6,000 years old, and to say otherwise was heresy. And, in the Western world at least, that typically didn't end well for you, because, the church didn't like it when you didn't particularly appreciate it when you questioned church dogma. So this would mean that the earth was very young, and that any fossils you could see within the rock record were probably the result of the Great Flood. So that means the whole thing's sorted, done. I should also point out that absolute linear time wasn't actually defined until Isaac Newton, from a scientific point of view. But the problem is that humans are naturally quite an inquisitive bunch. So in the 18th century, what we've got a lot of gentlemen scientists that begin to catalogue and codify the natural world. So these are people who are very well educated, they have lots of money and lots of free time. And so they had to find ways to entertain themselves. So, some people started looking at plants, some people started collecting butterflies, and some people started looking at rocks and thinking about the earth. So unsurprisingly, this led some to consider whether the church's age for the earth was actually correct. So one of the first documented scientific attempts was by a Frenchman called Georges-Louis de Buffon. And he assumed the earth had once been completely molten, which is correct. And what he did is he melted iron balls of various diameters, and he timed how long it took that molten iron ball to cool and completely solidify, because his assumption was that the earth was completely solid. And so by using these iron balls, he could then extrapolate to work out how long it would take an iron ball the size of the earth to cool down and solidify completely. And the answer is 75,000 years. So okay, not really the age of the earth, but much, much older than the church age. So some scientists tried using sedimentation rates to calculate an age for the earth. So they were working under the idea that if you can establish depositional rates for various sediments, then you can calculate how long it would take for any sedimentary sequence of a given thickness to form. So, so if you know that it takes, 1 million years for a 1 meter thick layer of sandstone to form, and you have 5 of them, well, that sequence of rocks must constitute 5 million years of time. So if you can then calculate the time it would take for the entire sequence of sedimentary rocks to form, well, then you have an age for the earth, don't you? So it's a reasonably, straightforward idea. However, it does have several problems. The first problem is that the rates of sedimentation can vary widely. Some sand, in some environments, sand is deposited very, very quickly. In other environments, sand is deposited very, very slowly. So it may take a lot longer to form a 1 meter thick layer of sand in one location than another. So using applying the same rate of sedimentation to all locations is unfortunately not going to work. They also didn't know how much rock had been eroded because there's no point on the Earth's surface where you have a complete sequence of rocks. Some rock has always been lost. And unfortunately, these early geologists didn't know how much rock had been lost. And so obviously that means they have a bit of a problem. They also didn't know how thick the sedimentary layers were before they were compacted and lithified. So in the case of a layer of sediment, well, the layer of sedimentary rock you form is not the same thickness as the layer of sediment. So for instance, in order to form a 1 meter thick layer of sandstone, you might need, let's say, 5 or 10 meters of sediment, which obviously you then compress and compact to make the sandstone. So this means that the layer, the thickness of the layer of rock they're looking at doesn't actually represent the original thickness of the layer of sediment. So that's another problem. And the final problem, and this one really is one they couldn't really get around, was you couldn't be certain what the total sedimentary thickness was for the crust. You didn't, there's no way of actually knowing exactly how much sedimentary rock is there. And so because there are all these uncertainties, it means that if you use this particular method, you can end up with an age of the Earth which ranges from between 1 million to 2 billion years old. So quite a large spread there. So in 1899, another attempt was made by a gentleman called John Jolly to calculate the age of the Earth, and he used the salinity of stream water and calculated how long it would take the oceans to reach their current salinity using salt contributed by rivers. And the answer is 90 million years. Now, once again, John Jolly's idea, on the face of it, seems relatively sound. However, he didn't know a couple of things. He didn't know how much salt was being recycled, and he didn't know how much salt was getting locked into, minerals like evaporites, or getting locked into, very clay-rich seafloor rocks. So the problem is that because you're losing this salt through these processes, it obviously means it would take a lot longer for the ocean to reach its current salinity if you were just using salt contributed by rivers. So his age is far too young. So the key thing to remember is that people were trying, and granted they were failing, but they were doing it in a scientific way to calculate the age of the Earth. But while the numbers were wrong, they were starting to consider how rocks formed and that the Earth was extremely old. So this then brings us on to James Hutton, who's often viewed as the father of modern geology. So in 1750 he moved to his family's farm in lowland Scotland, so he inherited it when his father died. So he became interested in the local rocks, and he became especially interested in them because he wanted to improve the quality of his land. And so in order to do that, he had to dig several drainage ditches to allow the land to drain more efficiently. In order to dig those drainage ditches, he had to cut through rocks. And so as he and his helpers cut through the rocks to create these drainage ditches, essentially what they ended up doing is they ended up creating nice, fresh, clean rock faces which he could look at. And so he began to look at these rock faces, and he began to see things in them, and he began to interpret them. Later on, he became involved with the construction of the Forth and Clyde Canal. And once again, this was a very, very big canal. And this once again gave him the opportunity to look at huge exposures of freshly cut rock. So he had these beautiful, clean surfaces where he could look at the rocks and try and interpret what was going on. So Hutton made several key observations, and these are very, very important, and they underpin modern geology. So the first thing he noticed was that sedimentary rocks formed through processes that were occurring today. So this is the principle of uniformitarianism. So what he realized was when he looked at sedimentary rocks, he could see structures and processes that were occurring in modern systems. And so he extrapolated and he said, right, well, these sedimentary rocks clearly formed through the processes that I can see happening today. He also noticed that sedimentary lithology, sedimentary rocks, were produced through the erosion of exposed rock by the action of air and water. So once again, he realised that in order to get the sediments to form these sedimentary rocks, something clearly has to be eroded. And so he looked around and he said, right, well, what's doing the eroding? And obviously air and water are the main mechanisms for breaking down rock. That also then means that the sedimentary rocks you're looking at are actually the result of the erosion of even older rock. And so this means that, the sequence of rocks you might be looking at are not as old as, not as old as the Earth. So you could actually only be looking at a very small piece of Earth history. There could have been loads of rock before that sequence, which has been completely eroded away and lost. He also noticed that some sedimentary rocks, including rocks like coal, were formed from fragments of animals and plants. So he began to spot these fossils, and he very quickly worked out that rocks like limestone and coal clearly have a very high organic. There's clearly an organic component to these rocks. He realised that sediments must be compacted and lithified to produce rock. So, he realised that the thickness of the layer of rock he was looking at was not the same as the thickness of the layer of sediment from which that rock formed. They had different thicknesses. Obviously, the sediment would get compacted and the layer you get would be considerably thinner. So he also noticed that once lithified, so once turned into rock, these sedimentary rocks must then be elevated above sea level. Now, Hutton assumed that all sedimentary rocks were formed underwater, and obviously when the rocks are underwater they can't be eroded. So if you want to erode rock to make new rock, you obviously have to take those rocks from underwater and get them above sea level. So he came up with a model in which the crust was pushed up above sea level, exposing those rocks, which can then be eroded to form new sedimentary rocks. Hutton also went and realised that granites were actually formed from liquid rock, what we would call magma, which had intruded a pre-existing rock. So up until that point, granites had been interpreted as having precipitated from water. Now, once he realised that granites were the result of magma, and he realised that he had to have some kind of mechanism to push his crust up above sea level, he came to the conclusion that that means the Earth's interior must be hot, and that will produce the magmas, which we see in the form of granites. But because the Earth's interior is also hot, it's going to naturally be buoyant and it's going to want to rise. So he came up with a model by which the mantle underneath pieces of crust would become hot. That mantle would naturally want to rise a little bit, and so it would push the crust above sea level so it could be eroded. And these are all very important observations. They are all, to some degree, very accurate even now, and they had a very significant influence on geologic thinking. So what Hutton was doing is he was viewing the Earth as a cycle. So it's a cyclical system. So in his model, rocks are eroded, producing sediments that are deposited in the sea. The sediments are then lithified. The resulting rocks are uplifted above sea level, creating new continents. These continents are eroded, producing new sediment, and the cycle begins again. So as I was just discussing, his model for this uplift was driven by the mantle underneath the crust being hot and pushing the crust up. So this model was termed Plutonist. So the question is well, why does this all become important? Well, if you have a cyclical model like the one Hutton is suggesting, well, that means the rocks that we see weren't the only ones created. There could have been an unknown number of continents created and destroyed before the rocks that we can look at now were even deposited and lithified. So this means the Earth could be absolutely ancient. Now, this was important for another scientific theory, and of course that scientific theory is Charles Darwin's theory of evolution. Because as soon as you can say the Earth is extraordinarily old, well, that gives you the time frames required for evolution to take place. And so Hutton's observations and the theories he produced from them ended up being extremely helpful to Darwin's theory of evolution. So when we are talking about sequences of rocks and the erosion of those sequences of rocks, well, you have to ask yourself, well, hold on a minute, how can you prove that rocks have been eroded to, create sediments? Well, the first situation is we can see it, can't we? We know that rocks are constantly being broken down. Mountains are constantly eroded, producing new sediments that get transported by rivers, etc., etc. But if we look in the rock record, we can also see indications of erosion having occurred. And this comes in the form of unconformities. So an unconformity is a surface which is part of a sequence of rocks that represents a portion of lost rock. So it means from a geologic point of view, as we've lost rock, we've lost time. So unconformities come in four varieties. The three most common varieties are a disconformity, an angular unconformity, and a nonconformity. So in the case of a disconformity, we have horizontally bedded rocks below, horizontally bedded rocks above, and the unconformity itself is undulating. It's horizontal, but it undulates. In the case of an angular unconformity, we have dipping rocks below the unconformity, we have horizontal rocks above the unconformity, and the unconformity itself is the contact between these tilted rocks and the horizontal rocks above. And then finally we have a nonconformity. So a nonconformity occurs between an igneous or metamorphic rock and sedimentary rock. So here's our sedimentary rocks there. Here's our igneous rock here, and this dark line represents our unconformity. So in the case of a nonconformity, what we're looking at is we're looking at rocks which were deep in the earth. They got pushed up, exposed, and they exposed for erosion. So erosion exposed these, so this became the surface of the earth, and then they dropped back down below sea level, and then they got covered in new layers of sediment. So in each of these three examples, the unconformity itself represents lost rock. And the only way we can lose that rock is by eroding it. So unconformities quite clearly show us that erosion has been happening in the past. The fourth type of unconformity is actually a little bit of a difficult one, is a paraconformity. So a paraconformity is what looks like this. So here's our unit of rock above, here's our unit of rock below, and here's the unconformity itself. So we have horizontally bedded rocks above the unconformity, horizontally bedded rocks below the unconformity, and the unconformity itself is completely flat. So you can't see that it's there. The only way you know there's an unconformity here is if you can date this rock and this rock. So let's say this rock is 75 million years old, this rock is 70 million years old. That means this unconformity here represents 5 million years of lost rock. So the rock that was there was eroded away and it's gone. And so Hutton realised this, and this was a very strong piece of evidence to say that, obviously rocks have to be exposed and eroded, and then new sediment is deposited over the top. It was showing his system of uplift, erosion, deposition, lithification happening. And so when Hutton was the first to explain unconformities. So up until then, unconformities had been explained using what's called a Neptunist theory. So essentially, they said that the unconformity represented the land surface at the time of the Great Flood. So all the sedimentary rocks above the unconformity, they were deposited by the Great Flood, and anything below the unconformity was essentially pre-Great Flood. So what Hutton realised, as I was just discussing, was that he realised these unconformities actually represent periods of uplift and erosion before new sediments were deposited over the top. And his prime example of this is Sickaire Point in Scotland. So here's a picture of Sickaire Point, and you can see we have essentially a sequence of rocks. So here we have some red sandstones, and you can see they are dipping. Okay, so they have been tilted slightly, but they are near horizontal. Now below these red sandstones here, you can see we have another sequence of sedimentary rocks, but you can see these sedimentary rocks are near vertical. So we know that these sedimentary rocks here would initially have been deposited as horizontal sheets. So clearly what's happened is the sediment's been deposited, it's been lithified to form a rock, that rock has been tilted, so our horizontal sheets are now vertical. Now that tilting was probably due to uplift, so this sequence of rocks got pushed upwards, and during that process of uplift the rocks got tilted. So then they found themselves above sea level, And this surface here, the unconformity, represents the land surface. So any rock that was above this unconformity got eroded away. This was the surface of the Earth at the time. And then these red sandstones got deposited over the top. Okay, these red sandstones would have initially been nice horizontal layers of rock. They've been tilted a little bit since, but you can see what was going on. And so Siccar Point is a wonderful example of an angular unconformity. So if we just go back, here's an angular unconformity. Layers of rock below the unconformity are tilted. There we go, tilted. Layers of rock above the unconformity are horizontal. There we go. So this is a wonderful angular unconformity. The unconformity itself is coming through here like so. So once again, this is a wonderful example of Hutton's theory that rocks are essentially, sediments are created, deposited, lithified, so turned into rock. Then that rock has to be uplifted, at which point it's exposed, it can be eroded, producing new sediments, which then go to form new sedimentary rocks, and the cycle continues. So now we know the Earth was formed a long, long time ago. However, in 1866, someone threw a spanner in the works, and that person was Lord Kelvin, who the temperature scale is named after. So Lord Kelvin was an extremely important scientist in the 19th century. So he was also the kind of man who was so well respected that he could destroy your scientific idea just by saying he didn't like it. So Lord Kelvin had spent time underground, and he knew the Earth's temperature increased with depth. So Lord Kelvin went and looked at the following features. So what Lord Kelvin knew was the diameter of the Earth. That one was safe. He knew that. He also knew how the Earth's temperature changed the deeper you got. So the deeper you go into the Earth, the higher the temperature becomes. Now this is called the geotherm. So what he did is he estimated the geotherm for the Earth's interior. Then he worked under the assumption that the Earth had begun as a fully molten sphere, which is correct. But that was an assumption he was working under. He also knew the melting temperatures of rock. So what he was thinking was, if I take an Earth-sized piece of rock, what's the minimum temperature I have to heat that Earth-sized piece of rock up to make it melt completely? So once he knew this, he would know the starting temperature. So he would know the magma, let's say, started at 1000 Celsius, and then from there it was just going to cool down. And he also assumed that the Earth was losing heat at a steady rate. So his model essentially said, right, because I know the melting point of the rocks, I know what the temperature at which the magma ocean would have started. And so all I need to do now is I need to work out how long it would have taken this this massive ball of magma to cool down and give me the conditions that I can see now. And so based on these assumptions, he calculated an age for the Earth between 20 and 400 million years old. Now, Lord Kelvin didn't really like Hutton's ideas, and so he tended to stick to the much lower end of the scale. You'll notice there's quite a large spread there, and that's because a lot of this, the stuff he's using in his calculations, is assumed. And so, he's guesstimating, and so that means obviously the numbers he ends up with are going to have quite a large range. So Kelvin's calculation did serious damage not only to Hutton, but also to Charles Darwin, because of course Darwinian evolution requires very long periods of time, and 20 million years just isn't enough. So Kelvin campaigned for his young Earth model and against uniformitarianist geology and evolution for about 40 years based on his calculation. But the problem is he was lacking one important piece of information, and that was radioactive heat. So what he didn't realise was that the Earth's interior was being kept constantly warm through radioactive decay. So his calculation assumed the Earth started at a set temperature and it just cooled down in a linear fashion to the temperature we see now. But it doesn't. So his assumption was wrong. So he assumed he produced a time that was way, way, way too short because he didn't account for the additional heat being put out by radioactive decay. And the person who pointed this out to him was John Jolly, the chap from a few slides ago, who was trying to calculate the age of the Earth using the salinity of the oceans. And so once he pointed out that Lord Kelvin's calculation was incorrect, that was it, mic drop. Lord Kelvin's young Earth model completely destroyed. I should also point out, by the way, if you want to know more about John Jolly, go and look at his Wikipedia page. The man was extremely intelligent, did some absolutely wonderful things, and it's extremely sad that he isn't a better known scientist. So take 5 minutes, it's worth it. Okay, so this is a great place to stop. So once again, stop the video, get up, have a walk around, take some time to relax, and then come back for part 2.